Hello, everyone. Last week, we talked about the requirement analysis phase with focus on modeling techniques that can be used in providing an analysis model as an outcome of the analysis phase, with focus on two different methodologies, either the structure analysis methodology or the object-oriented methodology. And we cover two main models that are widely used in structure analysis, including the system context diagram and the data flow diagrams. In today's class, we will continue on this with other two types of modeling techniques. In particular, we will focus on state machine diagrams and entity relationship diagrams. Let's now start the state machine diagram, in particular using UML notations. What is a state machine diagram? Keep in mind that to build a diagram that can monitor the state among entities to provide an outline of the behavior of a system, which mainly focus on the behavior of entities within the system. So the behavior of entities within the system is not only a direct consequence of just its input, but it also depends on its preceding states. So entities will alternate between different states. States are mainly related to the past history of an entry, which can actually best be modeled based on state diagrams. Commonly, we use what we call finite state machine diagram, or before it was called traditionally automa. So UML state machine diagrams, which I will focus on today, or sometimes we refer to it for simplicity, either we use state diagrams or state machine or even state chart. It will show the different states of an entity. So the focus will be on it is a behavior modeling technique. We focus on the behavior of entities by monitoring the states of entities. State machine diagrams can also show how an entity responds to various events. So we are looking to identify a state of entities, which will later be translated as the behavior of the entities moving from one state to another state, which can be generalized to the state of the system. But this is not the only thing that we can see in the state machine diagrams, but we can also see the response of each of those entities to various events, which consequently will be in terms of a transition between one state to another state. Keep in mind that the focus for the state machine diagram, or like behavior diagrams that can be used to describe the transitions of states of certain entities in a system, or even the system in total, the focus would be on UML diagrams that are widely used to model the dynamic nature of a system. So state machine diagram typically used to describe the state-dependent behavior of an object or an entity within the system. What is an object in specific definition? An object responds differently to the same event depending on what state it is in. This is behavior of an object. An object specifically is an entity of a system. State machine diagrams are usually applied to objects, but can also be applied to any element that has behavior to other entities. It could be applied to actors, it could be applied to use cases, even methods, subsystems, and even system in total. They are typically used in conjunction with interaction diagrams, for example, as sequence diagrams. Let's look to the following example. And afterwards, I'm going to show you why there is a need to develop a diagram that can describe the states of entities within the system, which could complement some other diagrams like sequence diagrams or even the class diagrams. In this example, consider that you do have $100,000 in your bank account, and the behavior of a certain function, which is the withdraw function, would be if the balance, the balance can be easily defined as the difference between the new balance is difference between the old balance and the amount that has been withdrawn, which is the withdrawn amount. provided that the balance after the withdrawal is not less than 0. This is true regardless of how many times you have withdrawn money from the bank. In such situations, the withdrawals don't affect the abstraction. The abstraction of the attribute value and, of course, the gross behavior of the object would remain unchanged. However, if we look to this problem in particular, we can see that the account balance would become negative after a couple of the withdrawals. So at this point, we are interested to monitor the behavior, not only the functionality of the withdrawal function, but also the behavior of the withdrawal function. So, which would be quite different based on the transitions of withdrawals. This is because the state of the bank account now has changed from positive to negative. In technical terms, a transition from the positive state to the negative state is now fired. The abstraction of the attribute value is a property of the system itself, rather than a globally applicable rule. For example, if we look to the bank account problem, we can see that the bank changes the business rule to allow the bank balance to be overdrawn by $2,000 as an example. Then the state of the bank account will be redefined at this point with a condition that the balance after the withdrawal must not be less than $2,000 in defect. As you can see here, it's easy to build the structure of the system based on the entities, but it's also important to see the transitions among the states of the entities or even the state of the system with different transitions that would lead from a source state to a destination state, or a transition from one state to another state based on a triggering event or a triggering action. This has created the need of state behavior modeling, in particular like state modeling, which has been widely used in different software development process. So state machine diagram, which is widely used using the notion of UML diagrams, it consider objects with behaviors and states such that the state of an object depends on its current activity or even condition. A state machine diagram, it shows the possible states of the object or entity, if we talk about the general word, and the transition that cause a change in a state. So we're looking for the states, which objects we are monitoring, and even the transitions. Each state is like a mode of operation for the object. A state machine diagram would be provided to describe all the events and states and transitions for a single object. And on the other hand, if we compare the state machine diagram with the sequence diagram, we can see that a sequence diagram describes the event for a single interaction across all objects involved, which is different from what the state machine diagram is providing. So sequence and communication diagrams, when we compare them to state machine diagram, we can see that for sequence and communication diagrams, they are used to show how objects interact to meet some system requirements. However, they lack information on how the system decides on what the right things to do based on the transition between the states. So that's why there is a need for the state machine or like state diagrams, which is called state machine diagram, as it's widely used notation in the UML modeling. So let's now go and discuss some of the fundamentals notations and components of a state machine diagram. I'm going to start by defining what is a state diagram. A state diagram is always a directed graph. So we have a start node and an end node where we know exactly where the starting location is, where the end location is based on a directed edge or a directed arrow. In a directed graph, normally we use the notion of nodes, but when it comes to state machine diagrams, we will replace the definition of nodes by states. And in graphs, we use nodes to represent entities, and we use edges to represent the movement between those nodes. In state machine diagrams, we're going to use the states to represent nodes, and we're also going to use transitions to represent the edges. So transitions, mainly we refer to it as those occurrences of event that has caused the action of movement between different states. So in the following graph, you can see an example of a state machine diagram where we have nodes or states. We have transition between states, and we even can define the boundary of the diagram, which we call the diagram frame. And we always have an initial pseudo state by which the state transition has started. This example is particular for an object door, in which we're trying to see a different state for the door. It could be either opened, closed, or even locked. And then we'd like to monitor the actions and the events that has caused the transitions between those different states. Again, in comparison to activity diagrams, we can see that the vertices or the nodes would represent the carrying out of an activity, and the edges would represent the transition of the completion of one collection of activity to the new collection of activities. So on the other hand, for the state machine diagrams, we are referring to entities and their transitions from one state to different states, specifically for one entity at a time. The state machine diagram, they have some fundamental knowledge such that at any point in time, the system under description or even the object under description is always in a certain state, which means that it would behave in a specific way in response to any event that would occur. Keep in mind that some events will cause the system to alternate states, so it would change its state, such that in the new state, the system would behave, it might be in a different way to different events. The most important purpose of the state machine diagram is to model the lifetime of an object once it is created to the point where it has been terminated. So state machine diagrams are really good at describing the behavior of an object across several use cases, which we used before to model the scenarios within the system and functionality within the system. Also, you need to use a state machine diagram only for those classes that show interesting behavior, regularly the main classes of the system. That's why, generally speaking, we always have state machine diagrams aligned with sequence diagrams and even class diagrams. So one important note about the state machine diagram is that they provide hints on which attributes are also necessarily for a given classes by monitoring the state transitions of those even attributes. Let's now describe each component of the state machine diagram separately. What is a state? A state is an abstraction of the attribute values and links of an object, such that set of values are grouped together into a state according to properties that affect the gross behavior of the object. Normally, we denote a state in the state machine diagram using a rounded cornered rectangle with the name of the state written inside such rectangle. A state is considered as a condition of being at a certain time. Object or even systems can be viewed as moving from one state to another state. A state could have actions, and we always have two types of states. The first one is called the origin state, and the second one is the destination state. The origin state is the state of an object before transition, while the destination state is considered as this state to which the object moves after the transition has been completed. If we look to the following graph, we can see we have 5 states. I'm going to call this 1 and a 2, 3, 4, and a 5. This is a source state. And at this point, this is a destination state. Sometimes we call it source or we call it origin state. The same as here, we might consider at this point, if we look to this transition between shipping and delivered, that shipping is the source or the origin state and delivered is the destination state. And we can also plot all the transitions needed, which would be described in the following slides. So this is an example of a state machine diagram that has 5 states, and we also have transition between the states. It's important to identify which state we start from and which state we are ending to, and what has caused this transition. If we are interested to see what has caused those transitions and what will happen when we move from one state to another state, let's talk about actions. States can trigger actions. What is an action? Action is considered as an atomic execution, which means that once it has started, no way to stop it. Or once it is started, no way that you could have any interruption to stop it or even to terminate it. For each state, we do have 4 triggers for actions. It could be either on entry or on exit, or do like while in the state, or even on a certain event. In the following figure, we can see the name of the state, and we have the triggers, entry trigger, due trigger, and exit trigger. And then we can see the different actions that will happen once we have those triggers or activities. In terms of state machine diagram notations, there are different notations that can be used. What I'm describing here is the commonly used state notations, in particular for defining a state. As I said, we always define the name of the state at the beginning in the rounded rectangle. And we also have to identify all the actions and the triggers. You can see that we could have action performed on entry to state. This is the entry activity, or the entry trigger, and then the action performed while in state, this is the due activity, and action performed on the leaving state, that's the exit activity. Also, it might be actions based on a certain events. So we call this the deferrable triggers, in a way that we can see that events, when they happen, they will trigger a certain action. However, event that doesn't trigger any state transition, it will remain in the event pool already. This could be used later for preprocessing, especially if you are interested to see the transitions of object to another state. So characteristics of the state machine notations. As a matter of fact, there are several characteristics of a state in general, regardless of their type. A state occupies an interval of time. A state is often associated with an abstraction of attribute value of any entity that would satisfy some certain conditions. And I'm going to show you this one, an example in the next few slides. Also, an entity changes its state not only as a directed consequence of the current input, but also it depends on some past history of the input. As we talked enough about states, let's now talk about transitions, which is a second major component in building a state machine diagram. Transition is considered as a jump or a movement between one state to another state. Normally, we use lines with headed arrows to describe the transition between one state to another state. A transition may have 3 main components. We first trigger, a guard, and an effect. Transition normally happens between the origin state or the source state and the destination state. And when we describe a transition, keep in mind we have to describe the transition based on those 3 elements: the trigger of the transition, the guard of the transition, and the effect of such a transition. a syntax of writing a transition, we always start by writing the trigger. We open a square brackets, and inside it we put the guard, and then we close the square brackets, and then we have a dash, and then followed by the effect. Transitions typically take place in response to a certain event that has caused the transition between one state to another. In the following example, we can see different transitions between two states. In particular, we have two transitions. The first is on bottom pushed, and the second is off bottom pushed. This example is related to building a state machine diagram for a printer. So we're interested to see different states of a printer. The printer could be either off or it could be either on. When the printer is off, and then there is a transition between off and on. If we clicked on the on button, this is the trigger. And once we trigger, we have a guard. I'm gonna give you more details about the definition of each one of those next. And then once we identify the guard or the condition, we will also list the effect of such a transition. As you can see, the effect of the on pushing the on button, we are gonna run the self-test on the printer, moving back from the on status to, or the on state to the off state would be through the transition of turning or pressing the off button. So transitions, as I said, the syntax of writing a transition starts by trigger, followed by the guard, and then finally the effect. What is a trigger? Mainly it's just the cause of the transition, which could be either a signal, or mostly we refer to events, or even a change in some conditions, such that the passage of a time. The guard, as part of the transition in the state machine diagram, is considered as a Boolean condition that may optionally be present on a transition and must be true in order for the trigger to actually cause the transition. Otherwise, it won't cause such a transition. Finally, the effect, which is a component in describing a syntax of transition in the state machine diagram, is the final action or the effect, which will be invoked directly on such object that owns the state as a result of the given transition. So as a matter of fact, we could have multiple effects. And if we have multiple effects in one transition, you just use the comma to separate them. As you can see here, we have two states, state one and state two, and we have one single transition, but there are two effects that could happen. So if you're gonna call event one, that's my trigger, here's my guard, condition, the Boolean condition. And finally, the two effects, I could either create action one or destroy action one. These are the two effects that will happen related to the object based on the transition from state one to state two. So far we've talked about events a lot. So what is an event? An event is a significant occurrence that has a location in time. We are monitoring behavior of a system, so we're going to always talk about different events that might cause transition or change in the behavior of the system. And as long as we are talking about events, we're always referring to time and even space. So event is considered as this significant occurrence that has a location in time and space and can trigger state transition. What are the main reasons for generating events? It could be generated by either asking for inputs or producing outputs, and even execution of a method. Maybe sending messages or receiving messages will cause an event, or what we see a lot is abnormal termination has caused the abnormality event, or even error handling and exceptions can cause event. What are the main types of event that we can see it in a system that cause transition between different states as part of modeling the behavior of objects or even systems? There are 4 different types. The first one is called the call event. The second one is signal event. The third one is a change event. And the last one is a time event. A call event normally occurs when a method or even operation in an object is involved. So a method has been called, so this is what we call a call event. A signal event, on the other hand, occurs when an object sends a signal to other object. That's why signal events may occur. A change event occurs normally when a Boolean condition is changed. The change event labels are always preceded by the keyword when. And you're going to see this a lot. We always use when, and then we put a Boolean condition inside such event to determine when exactly the state would change from one state to another based on a certain condition. That's why we call it a change event. Finally, the time event always occurs when a time limit has reached, and we're going to use those keyword to describe the time event labels. The most commonly keyword that we use it a lot is after. So you just write the keyword after, and then you open brackets and you put exactly the time limit by which a transition has occurred between the states. So if we focus on time and the change in event in particular, a time event appears after the expiration of a time period. And as I said, a change event occurs if a specific constraint is fulfilled or a condition has been satisfied. The constraint that we say it will be satisfied is a Boolean expression on a Boolean condition on a given attributes of the actual object under consideration that we study the transition among of this object among the different states. In the following example, that you will see that we have three states: active state, backup state, and ideal state. And then we have one time event and two change events. The time event that the transition between the backup state going to the ideal state after 10 minutes. And then you can move from the ideal state to the active state using a change event when number of users exceed 0. So this is my Boolean expression or the specific constraint that we're looking for based on the attributes of such object. If the number of users equal to 0, then there will be a transition between the active state going to the backup state. So this is another change event. So moving forward from states and the transition between the states and what triggered them, in addition to the events, there are two important states that we need to study. Those two states are called initial state and final state. The initial state is exactly entered when an object is created. We always have one initial state, which is mandatory. The initial state is always represented as a solid circle. This is the initial state. On the other hand, the final state indicates the termination of such object or the end life of an object. The final state is non-mandatory, is optional. The final state is indicated by the bullseye. So this is the final state notation. More than one final state actually may exist in the same state machine diagram. More description about the initial and the final states is given next. What is the definition of an initial state of the state machine diagram? The initial state is a state that that shows the creation of an object. We have another terminology for the initial state, which is called initial pseudostate. Keep in mind it always denoted by solid circle. And a transition from such initial state will always show the first real state of such object. On the other hand, the final state of a state machine diagram is always considered as concentric circles or the bullseye. An open loop state machine, if we do have a state machine that has an open loop, It represents an object that may terminate before even the system terminates. This is a very important notation when it comes to final states, that we could have either open loop state machine or we could have a closed loop state machine. An open loop state machine represents an object that may terminate before the system terminates. On the other hand, closed loop state machines doesn't have a final state. If it's the case, actually, then the object lives until the entire system terminates. So in the following example, which is the tic-tac-toe example, as you can see, we always have one initial state while we have multiple final states. Initial state is where the system has been initially, another system, the object is initially created, and then showing the transition, the first transition of such object. And we can see that we have normal states here. So these are traditional states. And we have three final states. We could have multiple transitions between the X and turn and the O turn, like this an tic-tac-toe or the XO game. So we could have multiple transitions from different states going to the same exit or the final state. While if it's X turn, you could just win. If it's O turn, you could just win, or there might be a tie. So steps in creating a state machine diagram can be listed as follow. First step, you would define the state that an object might be in, and then you will give a description to those states. And third, you define the state transition for one state to another. In addition to this, you define the events that trigger transitions and the constraints on such transitions, which is those guards. So to illustrate the main steps of building a state machine diagram, let's take an exercise. We would like to build the state machine diagram actually for bank account. The first step is to defining those states, which in return, mainly we focus on the possible meaningful conditions or situations that an object might be during its lifetime in a system. If I will simplify this state machine, just focusing on two states. The first one is an account with zero fund versus zero balance. And then I do have one initial state. The second step in building a state machine diagram is to describe such states. You need to tell others in more details about what those states are. So you have to provide a description to those states, which will be used for future references. That means they have to be well documented. And the third step is to draw transitions between states. So we always have a transition between the initial state and the first state in the system. And then if the account bank, they have fund, they could go to a zero balance. And if there is a deposit, if this is like a withdrawal, how we like always withdrawal, like you're gonna withdraw money, and then if you're gonna deposit, you would go back to have fund in your account, and then finally go to your exit or final stage. So in addition to draw those transitions, like exploring the possible transition, or we call them like the initial preliminary transitions, you need to define within those transitions the triggers, which means that you clearly have to clarify what events that would have kicked off such transitions. As you can see in the bank account, the transition between the initial state to going to the account with fund state was through a transition of opening a bank account. You could withdraw fund and stay in the same state, or you withdraw fund and even go to a zero balance state. If you deposit fund, then you would go to account with fund, and you can even deposit fund and stay in the same account. Finally, you move from a zero balance and the object is terminated if you're going to close your account. So the final state, the final step in building the state machine diagram, in addition to adding those triggers on the transitions, is to define guard conditions if we have guard conditions by placing those constraints that need to be met before a transition um, actually take place. That means you try to allow your transitions to be conditionals on a certain constraints by which the transition will take place. As you can see here, if the balance is always zero, then the state of account with fund can easily loop and stay in the same state if the condition is satisfied or my guard is balance greater than zero. Otherwise, if the balance is zero, then we're going to go for a zero balance. And this is very important to build your state machine diagram by not only listing those triggers, but at the same time, you list the guards. Let's move with another practical exercise that we are interested to build the state diagram for such traffic light controller. What is the problem? The normal sequence for traffic light, green light in one direction for a long period of time, typically should not exceed 25 seconds, followed by a yellow light, which typically takes 5 seconds, and then the red light, which typically takes at least half a minute. So if we are interested to build a state diagram, I can clearly see that we have 3 states. It could be green, or it could be yellow, or it could be red. And moving from the initial state always start by red light. And after 30 seconds, the red light will go to green light, and the green light after 20 seconds will go to yellow light, and the yellow light after 5 seconds will go to red light. So this is the state machine diagram to describe the traffic controller. As you can see, it's very simple here. We just have 3 states. It gets complicated if you have multiple states for one object. In state machine diagram, we can also see self-transitions. So what is a self-transition? A self-transition happen when a state can return to itself. This is most useful when an event is associated with such a transition. So as you can see here, if we are in the waiting state, after 2 seconds, we will be still in the waiting state. So this is where the state returns to itself. We could also have compound state. What is a compound state? Means a state could have other substates. Or the entire diagram may include substate diagrams. Going back to the printer example, it could be, the printer could be on, but it could be on doing nothing, or it could be on actually doing a certain job. So within the state on, we do have other states. The first one is idle, and the second one is working. So there's a transition between those substates within even the super state, which is on. And the transition between idle going to working means if there is a request or there's a transition by printing, by a print trigger, we'll move from idle to working. And when the job is completed, we go back to the ideal case. So this is, we call on a compound state. Also, within the state machine diagram, we could have concurrent regions. What are the concurrent region? Concurrent region happen when a state may be divided into regions containing substates that actually exist and execute concurrently. As you can see in the following state machine diagram that describe a state called applying brakes. Within this applying brakes, we do have two other states that actually execute simultaneously, like concurrently at the same time. The first one is applying the front brake and applying the rear brakes. And then in this notation, we just use a bar because now moving from the initial state, going to different states in parallel within the concurrent region, we need to split the transition into two states running in parallel. This is the notation that we commonly used for concurrent regions. And then once we apply the front brake and the rear brake, if you will terminate the object going to the exit or the end state, you need also to use the vertical bar to determine the termination. Using this notation for the vertical bar and arrow will determine that the fact that we have concurrent regions within the state. So back to the example, again, to continue this example on the concurrent region, we can see that the on, especially for the printer, we can see that the on state, it could be it could have actually two concurrent regions. The first one is doing a checkup on the papers. First, we have the trays empty. If you're going to fill the tray, we go to the full state, and then if the tray number of papers in the tray is actually declining, then the low message will be created going to the low state. And then if you fill the tray, you will go back to the full state. Otherwise, if the tray is empty, you will go back to the empty state. As you can see, this state transitions is concurrently happening with the printing procedure, like with the printing transitions. So ideally, we start by ideal state, and then when there's a request for printing, we go to the working state. Once this job is completed, we go back to ideal state. So you can see the state transition of tray checkup, in addition to the printing procedure. They are concurrently happening within the compound state on. So that's why it's important to monitor the concurrent regions. So this actually very important, because in this graph we can see concurrent regions, and we can also see two different states, initial states within each of those concurrent regions. And we can also see transitions from one concurrent region going back to even the initial states, which happens if you're going to just click on the off button. Generally speaking, in state machine diagrams, we see a lot of concurrent regions, especially if you have multiple transitions happening concurrently at the same time. And we also see pseudo for the pseudo states, like the initial state, we have a choice pseudo state. A choice pseudo state, on the other hand, comes out from branching, or if you have multiple conditions that will branch to different states. We use diamond with one transition, and then it will split later to two or more transitions. So instead of having just one initial state, which we normally call it the pseudo state, and then there's always one transition from the pseudo state going to the next state. If we have a choice pseudo state, that means we start from the same point, but we could have multiple branches going to different states. At this point, we are not using the solid circle anymore. We're going to use a diamond transition. And then from the diamond, we could have two or more transitions leaving from the choice pseudo state. In the following graph, we can see that we have the select message format, that's the state. And then from the pseudo state, it could branch from the choice pseudo state, we could branch actually to 3 different states, like creating voice message, creating SMS message, and creating fax message based on different triggers. That's why we used diamond instead of the traditional solid circle. So in addition to the concurrent regions, the compound state, the self-transition, the choice pseudo states, we also have history states within my state diagram. A history state is used just to remember the previous state of a state machine when it was interrupted. A history state symbol, which we use with H, meaning that it should resume where it last left off. In the following figure, we have one initial pseudo state, we have one exit or final state, we have three regular states compounded underneath the running state, and then when the power of off, this is a transition, we're going to go to the power of state. However, when the entire running state should be saved within a history notation, so when the power is off, we go back to exactly where the system was last left off. So state diagrams and specification, there are more information in addition to the states and transition that we need to cover when it comes to state machines. The first one is about inheritance. Inheritance mechanism allows to redefine the behavior of this class and the superclass and a parent and a child class. One important information you should know is that every state of a superclass object is also a valid state of the subclass object. So if we have two classes, a parent and a child, and we define a state for the superclass, this state is also valid for the subclass or the child class. The state diagram of a subclass can always be inherited into the state diagram of, from the superclass can always be inherited into the state diagram of a superclass. So inheritance is a way to redefine the behavior of superclasses and its children. So with this, I'm summarizing the state machine diagram. The notations of building a state machine diagram, identifying the transitions between the states by mainly defining the triggers, the guard, and the effects. Also, events commonly happen a lot to cause transition between states is very important, to define those events. It's also very important to study the concurrent regions, compound states, in addition to inheritance within state machine diagrams. As we talked about the first model in modeling behaviors of objects within a system or even the system using state machine diagram, now I would like to introduce you to the entity relation diagram. In entity relation modeling, we are interested in modeling those data aspects of a system. So we are not interested in modeling the behavior of the system. Rather, we are looking to those data aspects of the system. So it is a data modeling technique specifically used for analyzing software systems that employ databases. Entity relationship modeling use entity relationship diagrams that would describe data in form of entities, relationships, and attributes. So data will be decomposed into entities, relationships, and attributes. We use ERDs as a data modeling technique that helps in understanding the data aspect of the system. Keep in mind, the ERDs are not used to cover how the data is processed, more or less how the data is modeled in databases. Entity relationship diagram, it was proposed in 1976 by Pierre Chen. It described entities of data and how they relate to one another. It is considered as a data modeling technique that graphically illustrates an information system entities and even the relationship between those entities. Entity relationship diagram is a graphical representation of the data requirement for a given database. Normally, we use ERDs to describe complex databases. In ERDs, as I said, we are modeling data through entities, relationships, and attributes. Let's now discuss each one of those components separately. Starting by entities. Entities let's start again. Like there was like markers here. So let me try to write again. Here we go. So let's start by entities. Entities actually in an ERD, it could be a person, it could be a place, could be an event, or could even be an object. Normally we use nouns to describe those entities, and we use square shape to describe it in an ERD. When exactly we say this entity is a weak entity, that means it is an entity that depends on another entity in the same graph or the same diagram, which means it cannot be defined without attributes of another entity. Then we use double-sided square to determine a weak entity. So as you can see here, item on a purchase order. So order item is a weak entity. All of the attributes of the order item should depend on the order entity. So that's why the order item is considered as a weak entity. In addition to those entities in the ERDs, we'd like to address attributes. When we refer to attributes, we are referring to property or characteristics of entities. We are referring to relationships with other entities. What is an attribute? An attribute is more like properties, characteristics, specifications of those entities in the ERD. An attribute can have its own attribute or could even have composite attributes. So an address attributes could have a number, a street, and a city, and later a street could define it by a name or a number. So it could be a single attribute or it could be composite attributes. Also, underlying attribute is a key attribute. So we use ellipse to determine attributes in the ERD. If we have composite attributes, we use a composition level where we have first attribute and then a composition of other attributes. We could have underlined attributes like double-sided ellipses to describe a key attribute. Also, the underlined attribute to describe the key attributes, but if we have multi-valued attribute, we're going to describe it by double-sided ellipse. And this is exactly when an entity has more than one of the same type of attribute. If we're going to take an example for this, a teacher can have more than one subject. So that's why we say multi-valued attributes. Finally, to complete the ERD, we need to talk about the relationships within the ERD that are mainly used to describe how entities would interact. They are normally labeled using verbs, and as a matter of fact, they may be recursive. And we use a diamond shape to describe relationships. If the same entity participates more than once in a relationship, it is known as a recursive relationship. Example, like employee entity supervise another employee. So this is where we say it's a recursive relationship. So in ERDs, we always talking about cardinality. Symbols of relationships. In today's lecture, I will discuss with you different type of cardinality symbols. They are discussed in different textbook. Feel free to use either one of them, either by putting the cardinality as a shape of the transition or the relationship, or just put a number to allow the multiplicity and the cardinality of the relationship. If you're going to use this notation for the double bars, we refer to exactly one, which is mandatory. If you're going to use a circle in three small lines coming into it, we refer to 0 or more optional. If you're going to use a plus on a circle, means 0 or more. There's 0 or 1, that's optional. If you're going to use a bar and a 3 lines coming into it, we refer to as 1 or more cardinality, which is mandatory. This is notation in the textbook of by Jason and Bird Boston, Analysis and Design in a Changing World. I'm going to show you next different notations. Feel free to use either one of these. However, when it comes to cardinality, there are some modality that we need to talk about it. but let me give you first an example about those cardinality constraints, especially if we build like a school student relationship. If we wish to indicate that each school may enroll many students or even may not enroll any students at all, in this example in particular, we also wish to indicate that each student attends exactly one school, then the following diagram indicates this optionally and mandatory cardinality. So you can see here, each school enrolls at least 0 students. This is where we use this notation. And at most many students, there we use the three lines coming into the circle. And we use the double bars to indicate that each student at least attends at least one at most one school. This is for the double bar notation. So using whatever statements to describe the cardinality constraints, we were able to elaborate this in our ERD using the cardinality symbols. Again, with cardinality assumptions and multiplicity in our ERD, we need to talk about modality. Modality refers to whether or not an instance of one entity can actually exist without a related instance with other entity. When we say this is a not null modality, means that an instance in the related entity must actually exist for an instance in another entity. A null modality means that no instance in such a related entity is actually necessarily for an instance in another entity to be valid. If we're going to use a simple cardinality notation, you could simply ignore the other shapes to describe your cardinality. It's easy for you to use 1 to n when we refer to one-to-many relationships, or n to 1 when we refer to many-to-one relationships, or even m to n when we refer to many-to-many relationship. As you can see here, a circuit connects. So one circuit could connect 0 to n components. This is the simple notation of adding cardinality on the diagram. So let's take an example to actually help in building an ERD. A university consists of several departments. So now we have one entity and we have another entity, which is a department. Each department is assigned several instructors. He's a third entity. So where each who each teach one or more courses. So I see another entity. And then a student is a member of the university, so another entity. And the university consists of many students. So I'm just trying to highlight the entities, and then later on I will highlight those relationships and attributes. Each university students may attend one or more courses, and each course is taught to be by one instructor. If you're going to actually interpret this information to build our ERD, we first have to extract those entities. As you can see, a university, a department, instructor, a student, and a course. And then we're gonna draw those entities in a form of ERD notations: the university, the student, the department, the instructor, and the course. And then we add the relationships. So we are looking to those keywords that determine the relationships. This consists of several. This is assigned several instructors. A student is a member, may attend one or more courses, and then teach one of those more courses given by the instructor. If we're going to add those relationships using the notion of the diamond relationships, we can see that the university has many departments. We're going to use this word many later on when we add the multiplicity. A department is assigned relationship with the instructor, and the instructor teach a course. Students can attend courses, and university has a relationship is a member of a student. The way we put the multiplicity and the directions of our relationship determines actual the cardinality and the multiplicity of those relationships. So now, after we add the relationships in addition to the entities, let's now add the cardinalities. So you can see a university has many departments. Also, the department assign many instructors. The instructor teaches many courses. Many students can attend many courses, and the university has many students. So now let's complete the graph by adding attributes for each of those entity. Department, they will have a department name. The university has a phone number, a name and address. A student has a name and ID. Structure has a name and ID. And the course has a name and ID. Whatever you are building, a state machine diagram or even an ERD, it's very important to know what are the main business rules that should be applied, because later on you need to validate it to guarantee that you have an accurate analysis model at the end. Business rules for ERDs are those constraints followed when the system is in operation. As you can see here, when we add those multiplicity, we put a constraint that a customer can place 0 or more orders. This has to be validated in the SRS at the end. Also, when we use the double bar notation, an order must be placed by exactly one customer. This is a rule that should be validated in the specification phase. Or even you could do it at the end of the analysis phase before you even provide a more specification into the SRS document. In addition to the business rules, we also need to enforce referential integrity. What is referential integrity? Referential integrity is a property of data. When actually satisfied, we require that every value of one attribute, normally we look into databases, so these are columns of a relation table. We require every value of one attribute of a relation to exist as a value of another attribute in a different table, different relation in the table. This is the referential integrity between different attributes. Also, every foreign key value is considered as a primary key. The database management system, they enforce referential integrity automatically. You don't need to worry about it as a system analyst. After schema designer actually identify those primary and foreign keys. But it's very important to keep this in mind when you build the ERDs, because ERDs are always attached to databases. So it's important to address referential integrity, foreign keys, and primary keys. What are the main steps in building ERDs? In order for you to build an ERD, you look at it as an iterative and process of trial and revision, such that you start by identifying each entity, identify the entity attributes, then identify the primary key for each entity, identify the relation between entities, identify those cardinality constraints that we're going to add it on the relationships, and then finally the ERD, and check ERD for validation, which means we have to ensure that all the constraints added on the relationships to determine those business rules are satisfied. Let's now start by the first step, finding entities. That if you would like to find entities to be plotted in your ERD, you need to identify major category of information. If available, you need to check the process model that you built for data stores and external entities and even data flows. Next, you need to check the major input and output, and also check if there is more than one instance of the entity that would occur in the system. This will definitely help in identifying entities of a system. For you to identify entities, you always look into the database tables in which you have all the entities listed, and if they are not all inclusive, you have to extract them from the description and add them later in your database table. And in each table, keep in mind that you have the definition of each entity and its attribute. If we have the attributes defined, then we could proceed. If not, we have to add the attributes and even assign identifiers, which could be done by identifying entity attributes that are relevant to the system, and also check the process model that was originally built for details on data flow and data stores, check the data requirements for the requirement definition, and of course, perform document analysis on existing forms and reports, and select the entity identifier. After you add the attributes, it's most important to identify relationships, which actually begin with the entity. And other entities that might have a relationship with such entity. You need to clearly describe the relationship with the appropriate verb phrase and determine, in addition to the relationships, you need to determine the cardinality and the modality by discussing the business rules, of course, with your stakeholders. After you identify the relationships and you came up with extraction to those entities and the cardinality, it's very important before you proceed and plug your ERD into the specification document is to validate your ERD. So when it comes to the stage of validation, you have to go through all the entities in your diagram to see if all the entities are complete, all the attributes of each of those entities are well defined. The primary key of each entity is also defined or not. And the relationships are well maintained and described clearly. And the constraints of each of those entities, each of those relationship is accurately added to the relationships. This is an iterative process. Then you have to plot your entities with attributes and the relationships and then keep checking for validation. If it's valid, you could do trial one. If it's not, you do another trial until you have a validated ERD diagrams. So to summarize, the main tips to build an ERD: identify all the relevant entities in a given system and determine the relationship among those entities. An entity should appear only once in a particular diagram. You provide a precise and appropriate name for each entity and each attribute and even each relationship in the diagram. There are some notes you should be invoking them in your ERD to guarantee accurate, non-ambiguous ERD in a way that your terms should be simple, always familiar to the stakeholders. Try to avoid vague terminology or even technical sound words that may not be understandable by all of your stakeholders. In naming your entity, remember to use singular nouns. Also, you could use adjectives to differentiate between the same class. Like if you have employee and employee, you might want to use part-time and full-time to differentiate between them if necessarily. Also, if you would like to name your attributes, they must be named in a way to be meaningful, unique, system independent, and also easily understandable. Keep in mind, you are working with different stakeholders of different background. And most importantly is you need to remove any vague, redundant, or unnecessary relationship between those entities and never connect a relationship to another relationship. You connect entities to entities through relationships. So this is part one of today's lecture in which we have covered materials related to the state machine diagrams in addition to the ERDs, which are commonly used in building an analysis model that highlights on a behavior of a system in addition to data modeling between different entities of a system. I will stop here and I will start part two.